Thank you very much, Joyce. This is like possibly the coolest kind of way to spend a day, talking about light fields and things. It feels a little strange to be here at Stanford talking about light fields without Mark Lavoie somehow watching over us in some way, but given that he's now at Google and working on things like their camera projects, maybe he is at some point. Particular entry into light field imaging that I saw was through the field of image-based modeling and rendering, and light field rendering was one of the cool things that happened. In fact, it was such a cool thing that it basically spawned an entire new subfield of computer graphics and related fields called computational photography. And back when it was part of image-based modeling and rendering, it was a nice way to make your image-based models look better. So if you were modeling an object from photographs and reconstructing some geometry, and the geometry wasn't quite right, and you were using photos. This is a model I made of my car a long time ago, back in 1991. I used a volumetric intersection technique. I projected the photos back on, but as it turns out, the rendering algorithm that I hacked together actually had the property that depending on which direction you were looking at the car from, it determined which photos, either from the front or the back, or the top, that it would actually use for the texture mapping. So if you watch the windshield carefully here, you'll see that it fades from the photo from the front, which shows one reflection, to the photo from the top, which is a different reflection. As a result, you get a slight sense of the material properties of this model as you're rotating it around. You can see some surfaces are reflective, and that makes it a lot more realistic than just kind of like painted shoeboxes. And when I got to doing my PhD thesis at Berkeley with Jitendra Malik and C.J. Taylor later, we definitely were running the risk of creating painted shoeboxes by projecting photos back onto architectural buildings that we were photometrically reconstructing. And so the idea was to do something that we called view-dependent texture mapping, which is to choose which photos you're mapping onto the architecture, if you have multiple photos of it, based on your viewpoint. And so as a result, you end up with essentially rendering all of the surfaces of the architecture with a sparsely sampled light field. And when we made our animation of the Berkeley campus, which had pretty simplistic geometry actually, the photos, we had enough of them going around the tower, are actually being faded into and out of, and so all of the faces of the Berkeley Tower are essentially light field renderings that are happening, and you can kind of tell. It's a subtle effect, but it helps them not look like painted shoeboxes. And in fact, the time on the clock changes as you rotate the tower, because we didn't bother to go and get all the photos to be looking like they were at exactly the same time. So that basic technique of taking photos from multiple directions and then reconstructing models, projecting the photos back on through some students that we were working with at Berkeley ended up getting used to do some visual effects in the movie The Matrix. And it was done for the background. So they had photos of like on top of a building, and they projected it onto geometry. And there was a little bit of view-dependent texture mapping going on in there. But the cool thing is that they hybridized it with another thing that also resembles light field imaging, which is shooting the actor with a camera array and recording Keanu Reeves with views that were shot from all different angles with a whole bunch of Canon cameras. And so that's actually kind of similar to light field imaging. Of course, it's only a 1D array of cameras. And that's something that picked up on a line of work which actually had some earlier roots in Tim McMillan's work when he was doing an art degree at the Bath Academy of Art in the 1980s. So these are some of the camera arrays that Tim McMillan was creating, of course, on film. A single strip of film went behind a whole bunch of pinhole lenses here, and then he'd put off a flash that would expose all the film at the same time. He was careful to put the pinholes 4 perforations apart on the film so he could then just run it through a movie projector and then watch the movie of these kind of like 1D sampled light fields. Now, this is really cool to start recording the light fields of people, but if you're going to have a computer representation of a person rather than an environment, it becomes very important to be able to control the illumination. on people, because if you're going to try to put somebody right here, you need to light them the right way so that they look like they're right there. And we started thinking about that as kind of the last project that we did at Berkeley back in the day, about how a person not only emits a light field coming out, but also is illuminated by a light field going in. And we called the combination of how a light field going out is created by a light field going in as the reflectance field. And you can actually represent all the ways that a three-dimensional volume seen around from a surface reflects light as the reflectance field. And in order to start capturing this, we started building spheres of lights that could illuminate people from different directions and try to record slices of this reflectance field, how a person looks from all different directions and how they reflect light in a variety of directions. So a very basic process that we could do is, for example, film somebody with a high-speed camera and then rapidly change the light on them from all the different directions that we have LEDs, and then we get this kind of time-varying, we call it a 4D reflectance field, because we have 2 dimensions of illumination everywhere that it comes from. And then we have a 2-dimensional image that shows that. So this is a friend of ours named Lucas who's delivering a line of dialogue, and we're able to see him in about 30 different lighting directions as he gives exactly the same performance, because we're changing the light on him 2,000 times per second. And this is kind of fun to watch how the face looks different when it's lit from different directions and gives a different emotional feel to it. But it also becomes a nice data set that you can then use to relight him under arbitrary illumination environments where he's got different colors and intensities of light coming from all the different directions. So this is that exact same performance, which is virtually re-illuminated by the light of Grace Cathedral. So this is a kind of a 2-dimensional infinite light field impinging upon him. And there's kind of, bright yellow light coming from that direction on the right. So we added the images that were lit from that direction together. We tinted them bright yellow, and then we added it to all the other directions of illumination, tinted and scaled according to the color of the light in that environment in order to render him there. Now, both of these things, the image that's coming out is, just a 2D image. We don't have a full 4D light field there. And also the image of light going in is also a 2-dimensional light field. So it was something that was definitely interesting. Let's try to record incident illumination as a full 4D light field. And let's also try to figure out how to then display it onto somebody. And so we got interested in that shortly after. And what we did is we set up a spatially varying lighting situation in one of our cleared out conference rooms. So we have some spotlights, we put some occluders in here, and then we built a gantry that has a fisheye lens, and we'd scan across this area of all the places that the light would fall, and you see it's lit differently as it moves around. And each one of these images, this is a time lapse, this took like all night, and we had to finish before sunrise or else the data set was messed up. And all the images were shot in high dynamic range. So we actually have all of the correct pixel values up to staring directly into the spotlights. And then the images, if we just look at kind of one exposure that's coming off, or these 180-degree fisheye light fields, that's the full dynamic range of the illumination. And then the idea was, well, let's try to light some computer-generated scenes with this spatially varying 4D light fields. And we were lucky to have some experience using Greg Ward's Radiance program. Jonas Unger, working with us, hacked in a light field shader for that, so we could try to match a computer graphics rendering of some computer-generated objects to real versions of those objects that were actually sitting in that illumination. So you can still see the gantry that was holding the cameras here. We took the camera off, we put this little table on top of it, photographed some real objects by the light, and it turns out you can get just about all of the effects of spatially varying illumination impinging on those objects. It's limited in resolution. If we had very high-res detail in the incident light field from, say, some plants that were in front of the light source there, then it's a little pixelated when we simulate that incident light field as well. So increasing resolution, as Kurt was talking about, is definitely of interest. The other thing that was a drawback to this technique is that it took a long time to record that light field. So another thing we explored in that work was single-shot light field capture. And we got a whole bunch of pinballs, which are pretty cheap, and glued them to a board. And then one photo of this device here, and the reflections that you see actually gives you a whole bunch of almost fisheye views of the scene. And so you can actually use this as a data set if you shoot in high dynamic range to illuminate a computer-generated scene with spatially varying illumination. And then another paper that came out that year that was done by Phil Dutre's group, Macelas et al., showed that you can actually take a 4D light field and use it to illuminate real actual objects here. So they built this clever gantry where they have a video projector, they can rotate the objects around here, they have a camera, they can put the projector at all different angles. And so they actually recorded, pretty low resolution, but they got the point across, the effect of four-dimensional incident illumination on real objects by adding together different images. So we continue to think about ways of crossing light fields of illumination with light fields of objects that you can really see. And we're particularly interested at our institute in actually creating digital renderings of people that you can eventually interact with. And one of the projects we did tried to do this for actual real-time performances. So using one of our larger light stages here, this is light stage 6, it has about 1,000 different directions of LED illumination. We got Bruce from our laboratory to walk and eventually run on this treadmill as we slowly rotated him around. And we filmed him with high-speed cameras. We had 3 of them. And if we slow down the footage, you can see what we were really recording is for every one of the directions on him, we got an entire lighting basis. So we have him lit from all different directions. And since we slowly rotate him, we see him from all different directions going around in the circle. And since we had 3 cameras, one above, one at waist level, and one at floor level, we effectively had 108 images of this relightable light field, which varied over time, which was a 7-dimensional function. We also got a transparency mat for the background. And at this point, we had a data set of a person that involves no geometry whatsoever, but it's relightable, and we have control over the viewpoint as well. So this is a real-time light field rendering of Bruce, and you'll notice that he kind of shifts around a little bit as we rotate around his light field, because each one of those positions that you see of him going around is the result of him returning to the next place in the walk cycle on a separate one of his steps, and not quite coming to the same position. But the cool thing is that when you see this in motion, you actually don't notice those effects. And so we can also do this in motion and choose the lighting. So if our goal is to make it look like Bruce was running across this town square in Pisa, and we've recorded the illumination there with a light probe image, then we can actually light him the right way, get the right perspective effects of his coming toward us, going away from us. We can give him some company. And with some work that Alex Ma did, we actually did a volumetric reconstruction of him to get basic geometry to cast shadows on the environment. But there's no real explicit geometry of him, and it kind of looks like Bruce, and that's a good thing. Joyce is very nice to mention one of the awards that we won, that the light stage technology won, and that actually posed another light field issue for us, which is that we really wanted to keep it in our laboratory, but the Institute said it has to go in the main display case downstairs, and that they also want us to send a copy of this thing to our sponsors so they can enjoy that as well. Or you're not allowed to make copies of these things. So we thought, well, let's try to take a light field of it and then send them a light field of that. So we actually put this thing here. We lit it with some softbox lighting, which is kind of the right way to illuminate reflective surfaces. And then we used our gantry to shoot an entire light field of this little award thing here. So the camera is moving back and forth. We have some calibration markers there that are going to tell us where it is. And instead of rotating things and moving the camera in strange directions, we just took a wide field of view lens, a very high resolution camera, and then just scanned it linearly around to make a lot of the math simpler. And then by rectifying it, here you can see that now we basically have the main plane of this thing fixed in place, and then all that's happening is that the depth information is revealing itself. Now we had to display the light field as well and actually give people something there, and so since we didn't have one of Gordon's cool displays around to send them, we actually got in touch with our friends at Zebra Imaging, which make holograms. And in fact, if you give them a whole bunch of Hogels, which are images that are 512 by 512 representing a 90-degree field of view cone of light leaving your surface, they can actually print them onto holographic film in a way that you can see that. Now the thing is, we took a 64 by 64 grid of images. That's 4,000 images and about as much as we were willing to wait around for of this thing. But the Hogels are 512 by 512, so we had to upsample this. And the problem is if you just do that using linear interpolation between the images, it's going to blur things out because it moves enough from image to image that you won't be able to read the details and such. So what we did in order to create the Hogels for this hologram that we wanted, is that we did a rough three-dimensional model of the surfaces of our object, and then we refocused the light field onto that in order to create the Hogels. So whereas normally in kind of traditional ST plane, UV plane light field rendering, we would have gone to every one of these places on the hologram plane and then just looked as to where it projected into the two closest cameras. From there, we instead actually trace it to our camera ray back onto this surface and then into the cameras. So it gives us a corrected version of that. And now when you take multiple images together, it actually brings parts of the light field into focus. That's another thing that was explored in the Lumograph paper by Gortler et al. And it's a really good way to do holograms. And so this is the hologram of the thing. And you can actually get in there and see all of the different surfaces in a way that it's sharp enough to see what's going on. And it's really cool. You can see the reflections of the stuff in the plaque as well. So having holograms hanging on your wall is useful for a lot of things. Another thing that you could do with holograms is to have them possibly be something that you can look at in a virtual reality headset. And some work that's going to be demoed later by Otoy is taking this concept further. What they're using is their global illumination renderer called Octane, which can produce very realistic imagery with lots of bouncy light transport and different material properties and such. And it runs really fast, but you'll see that this is all interactive rate global illumination. That's impressive. But unless you wait like a couple of seconds for it to stabilize, it's still kind of noisy. And that's only rendering one view at a time. So what they've been doing is pre-rendering light field slabs with great global illumination rendering. I think this is something Greg Ward was playing around with in his holodeck paper a while ago. And they get these kind of like windows into this global illumination world that you can move around interactively. And they're doing some really clever things, because you'll notice you don't see the traditional light field artifacts that you can of limited resolution or limited depth of field. And they can play it back in real time. So this is actually using the tracker from a Oculus Rift dev kit 2 to look into this light field that's being displayed on a screen. And you can look around in this global illumination scene. It looks considerably better than the real-time computer graphics that we're used to seeing. So that might be a good way to generate content for these VR displays. You also might want to have a real-time, interactively updatable light field that you can see right in front of you. And while there is some work going on trying to create automatically updatable holograms, the University of Arizona is leading, and I think they can update their hologram twice per second at this point. it's not the most practical thing right now. We got to collaborate with Mark Bolas and Ian McDowell at Fake Space Labs a while ago in a way that was using high-speed video projection to try to create at least a horizontal parallax-only light field. So this is a device we showed at SIGGRAPH a while ago. It has a video projector that's going to be straight from above. It'll reflect onto this anisotropic display surface. This will rotate around at 900 RPM, and it's synchronized to the video projector images so that when that spins up, you'll be able to see a three-dimensional floating-ish kind of image. And it's kind of cool because it spins fast enough that the display surface becomes pretty much transparent, so it kind of looks like it's floating in space. We're really sending independent images of the scene in all different directions, so we get occlusion, unlike some volumetric display techniques that are out there, and you don't see one side of the head ghosting through the other side of the head. We were able to run this all in real time from an NVIDIA graphics card, which was somewhat overworked, but able to do the 5,000 frames per second required for this. And once we had this little head on here, we, of course, wanted to eventually be able to talk to that head. And so we did another project to try to create a three-dimensional teleconferencing system using this light field display. So this is a rendering of a Jillian here. She's in another room, and she's getting a live 3D scan of her face, and then that's being displayed on the spinning display surface. We made a little bit larger one of it. We got to 2 video projectors that could kind of do 2-channel colors, so she's looking a little bit better than black and white here. And the cool thing that was nice about this is that this person here, now that they're displayed as a light field, could actually look around the people who came up to talk to her and make eye contact with them. And when Jillian looks at Magnus, he actually thinks that she's looking at her. And Andrew knows that, okay, those two are having a conversation, so I can kind of sit back and just watch what they're doing. But as soon as she looks at me, time to pay attention. And that's something you don't get in a Skype chat or FaceTime currently. Well, we had some good luck with this. We thought maybe it would be fun to eventually scale this up, but there's actually a significant amount of mass that's spinning very quickly. And that's probably not the safest thing to have in the home or try to make a lot of. So we eventually thought, okay, well, we should go ahead and unfold the optical path. The reason it works is that if you think of this display surface as a mirror, and that's essentially what it is in a horizontal slice, we're putting a ton of video projectors in a row that are aimed into you. And as you saw in the Lippmann work, the idea of having a whole bunch of video projectors aimed at you to create a three-dimensional image is not new. Here's another nice example that Mark Lavoie helped me research, which is from 1976, which shows an array of video projectors going into a screen to create an auto-multiscopic image. This is just showing a 1D array of projectors. Of course, what we'd eventually like to do is have a 2-dimensional array of projectors where every projector is now an angularly varying pixel, and you can create an image that way. So if we eventually have, tiny micro projectors and we can put them far enough away from people, I think we'll have some awesome light field displays. We did some tests to figure out just how far apart the projectors need to be to get a good image, and I think the main conclusion is that the smaller the projectors and the closer you make them, the image keeps getting better and better. So we, for our first version of a projector array, got the tiniest little projectors that we could get, packed them as close together as we could, so we have to put all these little fans on them. And this is Andrew Jones and Koki Nagano looking into our projector array, which we'd eventually take to SIGGRAPH 2013, and it's playing back a sequence that was recorded in a light stage of a three-dimensional geometry of a face. And here this is horizontal parallax only, so it's not real light field rendering, but something that we did here is we actually put a Microsoft Kinect looking back into the audience, and it's tracking the faces of all of the people who come up to look at this display. And once you know where people are, how far away they are, and where they are in height, you can actually adjust your renderings of the scene so that when the projectors or the parts of the projected images that go toward this person are actually rendered from that person's height and distance and get appropriate perspective effects. So you can see that as you move back and forth, if it's not tracking you and you just kind of fix what it was doing, you'll actually see the object tilt up and down as you go back and forth for that. So in this case, it's tracking that gets you the vertical parallax, so there's lag if it's not fast enough. But mostly people are more likely to move left and right quickly, and of course their two eyes are simultaneously in different positions than they are to jump up and down, unless you get them really excited about what's on the light field display, and then they're probably going to break the tracking algorithm. So we've had a chance to take this a little bit further at this point. We've built a somewhat larger device, this is a capturing of a fellow named Morgan Spurlock for his CNN show. We're filming people with about 30 different points of view. And from these, Kurt mentioned before that when you're recording, you can kind of put the cameras wherever you want and then eventually figure out what the scene was. But when you're displaying, you really have to create the light from all the proper directions. This is our projector array. We have 216 of these pocket projectors, and we use view interpolation to interpolate up the angular resolution of the images from the 30 video cameras that we're recording with to the 216 video projectors. So this allowed Morgan to
just when you thought it couldn't get
have a conversation with himself
suddenly,
here.
It did.
Let's see how much like me you really are, all right? I'm going to ask you some questions that only I would know the answer to.
Sure, go ahead, ask me some questions.
What's your earliest memory?
I think it was a few months before I turned 3 years old, and we had just moved to our new house in Beckley, West Virginia. And I remember moving men unloading the truck, and I can see myself walking across the lawn towards the moving truck.
So this is a little bit of a vision. Let's see if I can go back and show what it looks like when you change the angles here. So this is the imagery from if you look at all of the projectors, they're all showing different views of Morgan. And if you move this card out toward the display, this is just a diffuse card. So when you finally get them in the focus of the projectors, you see a very shallow depth of field view of image of him. And then it goes through this anisotropic display surface. So this is showing some of the horizontal parallax that you get by moving back and forth. And we can play that back. So just to conclude, that was all shot with a 1D array of cameras, 30 cameras, so we don't have the vertical parallax. And it's also shooting a person rather than an environment. And when we think about what's going to be the ultimate content to put in the next generation of virtual reality displays, this is probably like the right kind of thing to put at the 50-yard line of a football game and then be able to have all the data you need to put your head in that great seat and then look around and get that parallax, which Kurt explained was so important. But to even do it at vaguely acceptable resolution, maybe you need about 128 cameras, and that's going to generate a gigapixel per frame, and you probably should have 60 frames per second. So I think we can safely say that there's at least another 10 years of good research to figure out how to build the circuitry that can compress this in real time to represent it as a decompressible light field and then stream it onto VR devices, which very well might need to just be a mobile device that's getting this stream in there. And that's going to be fun because I think probably people in this room are going to figure it out, and then we're going to have much better seats at our football games. So thank you very much, and thanks to our organizers.